All right, hi everybody. We are going to take what we were looking at with correlation. We're going to take it one step further and look at creating a linear regression. A regression is a model that we use, an equation that we come up with that tries to fit the data as best as possible. It's not going to be a major step for us today, but I do want us to understand some of the mathematics that's happening behind this. Again, just like the correlation coefficient R, I'm not going to give you the formula to how to calculate our linear regression, but we are going to understand a little bit of how it works. So what I have here is I have a scatter plot with some different points, and I have a line drawn in. Now, when I draw in any line here, what we do is we measure the distance that each point is from the line. Now, we don't measure the shortest distance, we just measure the y distances. We look for that difference between the y value of the point and the y value of our line. And that distance is called a residual. Okay? So they have all these residuals. Okay? Now, if we want to make the best line possible, we want the residuals to be as small as possible. However, we have one issue with this, and that some of the residuals are going to be negative because they're underneath the line, and some are going to be positive. And what happens when we add positive negatives? They just cancel out. So what we end up doing is we end up squaring the residuals. Okay? And squaring them then makes every one of those positive. And then what we can do is we can look to make that number the smallest that we can. And again, I'm not going to get into it much more than that, but think about as I draw different lines, okay, we have different residuals. And we are going to find the least squares line. It's called the least squares because we're squaring those residuals. We could try to eyeball it, and I'm guessing that you've probably done that when you were younger in some of your earlier math classes where you did a line of best fit. There's another term. So linear regression, least squares line of best fit, where you probably just tried to take a ruler and match it up as best you can. Well, here we're going to be finding the least squares line using our calculator. Now, the equation of that least squares line is going to be called y hat. I don't know why that hat looks like it's flying off here. Y hat equals a plus bx. Now, a plus bx, we should recognize it looks like the equation of a line, y equals mx plus b. A is our y-intercept, b is our slope. We just use some different letters here. Y hat, and the reason that we use y hat is because this is going to be our predictor. Okay? It makes our prediction of what the y value would really be in our population. And we've used that hat notation before when we've talked about point estimates, where we're using something from a sample to estimate something from the population. And that's kind of what we're doing here is we're using this least square line to make a kind of like a point estimate for the population. Okay? So, okay, let's look back at our chirping crickets. Okay? And let's find the line of best fit. And you probably already saw this happen in our previous videos when we just looked at correlation coefficient. We're going to do the same thing. So let me grab my calculator. Got to be somewhere here. There it is. And I have the chirping data in list 1 and list 2. So just like in the previous video, I'm choosing temperature to be X and our chirps to be Y. So I have temperature in list 1. I have chirps in list 2. I am going to go to my window. I haven't adjusted my window yet. And let's go 0 to 90. And let's go by tens. And then for our chirps, let's go 0 to, what was our biggest? Number of chirps, largest was 44. So let's go to let's go 60. Let's give ourselves plenty of room. And let's go by tens. Okay. So here's the graph. A little bit different just because I wanted to see the origin on this. And now what I'm going to do is I'm going to go to the same place that I went before. I'll go stat, calculate, and I'll choose linear regression. Looks like ax plus b, which is a little bit different than what I wrote here, so we have to be careful, but shouldn't be a big deal. I'm going to choose that. List 1 for my x's, list 2 for my y's, no frequency list, but this time I'm going to choose to store my regression equation into y1 so I can graph it and I can see how well it fits the line. So to do that, I'm going to go vars, yvars, function, y1. Okay, and that's going to take this regression equation that's going to pop up in the screen and automatically put it into y1 for graphing. So let's hit calculate. Here it is. Okay, now it goes out a long ways in decimals. Here's that correlation coefficient we saw before of 0.95. But we see that this in here, the slope is 0.79 and the y-intercept is negative 20.97. If I go to y equals, notice it already put it in there with all those decimals, and I can hit graph and we can see where that line falls. All right, so let me see. Of course, I lost it now. I'm going to have to do that again. Here we go. Let me just take a picture of this so I can write down the equation. All right, so our equation is going to be y hat equals, I'm not going to be picky if you do the y-intercept plus the slope times x, or if you do the slope times x plus the y-intercept. I'll actually switch it to this way just because our calculator does it that way, 0.79x minus 20.97. Remember your hat because we can use this to make a prediction now. So let's make a prediction. Okay. I want to make a prediction. Remember, x is the temperature at a certain temperature. So let's say that I want to make a prediction for a temperature of, I don't know, 30 degrees. So I can substitute 30 into this and get my value. So y hat would equal 0.79 times 30 minus 20.97 gives us y hat equals, so I could type that in my calculator. I'm actually going to come back here and I'm going to quit out of this and I'm going to go vars, yvars, function, choose y1, and I'm just going to put parentheses 30. It's going to say y1 of 30. It's going to substitute that in. And what do I get? 2.76. Okay, and that would be our prediction. That's how many chirps that we would predict at a temperature of 30 degrees. Okay. What are your thoughts on that prediction? Okay. Here are my thoughts. My thoughts are at 30 degrees, we are below freezing, and I don't think there is going to be any chirps from any crickets. We will not hear them when the temperature is freezing, right? Okay. So I don't think that we have a great prediction here. What if I would have put in 0? Well, if I would have put in 0, our y-intercept would have been negative 20.97. Are we going to hear negative number of chirps when our temperature is 0 degrees? Of course not. So this is going to lead into our conversation about making predictions. Okay? We can either interpolate or extrapolate. Okay? Interpolation, okay? We are making a prediction inside the data values that we have. So looking at the domain and range, okay? And if we make a prediction, so here's our scatter plot. This is, again, cricket chirps and temperature. They have their axes switched than what we decided to do. That's okay. And they made a prediction here for 30 chirps and a temperature of, I don't know what that is. It's close to 70 or 65 to 70. Notice this prediction is within all these points that we have. Okay? That would be a good prediction. We would feel comfortable with that. However, making a prediction way down here that's so far away from the rest of our points would not be a good prediction. We like interpolating, not extrapolating. Okay? And you hear that a lot right now, especially in this COVID stuff, to tie this right into what we're all experiencing. Hey, we are getting this data real time from our COVID-19 pandemic. And we're making models. When I say we, of course, it's not us, but scientists are making models to predict what's going to happen. However, the issue with this is all the predictions are extrapolations. Okay? They're extrapolating out into the future beyond our given data. So it's really hard to feel confident in our prediction that far out. So just something to try to tie into some of your minds, that we have to give these scientists a little bit of a break because they are trying to make predictions outside of the data values. Okay. So going back to this one, I would feel comfortable predicting the number of chirps for 76 degrees, because 76 degrees is falling in our domain here, isn't it? Right? Biggest is 80.5, smallest is 52. I would feel really good. I would feel good too about making a prediction for 50 degrees. It's not that far outside. But however, 30 degrees is nowhere near where we're at. Okay, let's do another one. Okay, let's go back to our GDP and CO2. Find the regression equation. Going back to my calculator, okay, I chose just to put these into list 3 and list 4, so I didn't have to delete list 1 and 2 again. So I have list 3 and list 4. I am going to go to stat, calculate, oops, wrong button, stat, there we go, calculate, linear regression. This time I'm going to choose my x's to be in list 3, my y's to be in list 4. I'm going to choose to store my regression equation. I already have one in Y1 and maybe I'll want to use that again. So I'm going to choose to put that into Y2 instead. And let's calculate. Here we go. So our least square lines, our linear regression, our line of best fit is going to be y hat equals 166.90x plus 115.72. So can we predict the expected CO2 commission? I don't know why I keep wanting to say commission. CO2 emissions for a GDP of 2 million. 2 million is the X value. Let's substitute that in. I'm just going to have my calculator do that. I'm going to go vars, y vars function, y2, parenthesis, we are substituting in $2 trillion, so that's a 2 right there. And our emissions would be predicted to be 449.53. And that would be millions of metric tons. There we go. All right, that's going to wrap up the video. What you'll be learning next will be how confident are we in this answer? We already talked about determining if the population correlation coefficient was significant. Well, how good is this prediction? Can we make a confidence interval? So we're going to look at some of that in the future, but that's going to wrap up this video. Thanks for watching. Have a great rest of your day.